Let's share the screen. And अच्छा, हाँ जी स्क्रीन शेयर हो रही है बेटा? शेयर हो?
Yes, sir.
Yes, sir.
चलें, ग्रेट। ओके जी, लास्ट टाइम हम लोग देख रहे थे फ्रीक्वेंसी रिस्पांस ऑफ द सिस्टम। सो एनी वॉलंटियर हु कैन टेल मी हाउ वी कैन गेट द फ्रीक्वेंसी रिस्पांस ऑफ द सिस्टम? जी जी बेटा, एनी वॉलंटियर? नो वन?
Sir, by taking discrete time Fourier transform of impulse response.
Great, zabardast. So this is one way of doing it. What's your name beta?
Sir, Yusuf.
Yusuf, thank you very much for answering, and it is correct. This is one way. Um, and along with that, we said that complex exponentials are the eigenfunctions of the LTI systems. And what is eigenfunction? Whenever we throw in some complex exponential or eigenfunction to the system, the eigenfunction will come as it is, and that would be scaled. So one way of doing the frequency response of some system is that, as Yusuf said, that you take the h of exponential j omega formula, DTFT formula, and use it and get the frequency response of the system. And the second way is that you throw in exponential j omega n to your system. This exponential j omega n will come as it is, along with some scaling factor, and that scaling factor will be the frequency response of the system. We have talked about this and we did certain examples as well. डाउनलोड करके देखा था, इसको पढ़ा था, सॉल्व की थी ये एग्जांपल्स? So these were different examples, and we were interested in knowing the impulse response, frequency response of these systems. So if we take this example, y of n is equal to x of n plus 1 plus x of n minus 1, that's nothing but the impulse response के context में अगर हम देखें, so that's the impulse response of the system. And we can directly use this formula, as Yusuf said, that we can use this formula. Okay, so we can use this formula h of n exponential minus j omega n, and n is equal to minus infinity to infinity. So we can use this formula, and we can calculate our frequency response of the system. And remember, don't leave your answer to this part. Always take it to this form, into cosine or sine format. Okay? Or that's the magnitude. If I'm interested in knowing the magnitude response of the system, that's the magnitude response, which is the real component 2 cosine f omega. But if I'm interested in knowing the phase response of the system, then there is no imaginary j term associated with that, so that's why the phase term is 0. Similarly, you can use the same thing as in this way as well, by making x of n is equal to exponential j omega n, as exponential j omega n is eigenfunction for the LTI systems whose impulse response was given. So what is y of n? It was given as x of n plus 1 plus x of n minus 1, and you have just replaced n with n plus 1, and exponential j omega n plus 1 plus exponential j omega n minus 1, and you have reached to the same solution, where your magnitude response is 2 cosine f omega and your phase response is 0. Similarly, there was another that was a simple delay system. Okay, suppose x of suppose nd हम suppose करते हैं, that's this is your impulse response to the system, and that's suppose nd is equal to 2. Okay, so that's your impulse response of the system. Okay, and that's the system. Suppose this is my x of n. What will be y of n? G. Any volunteer? Yusuf.
Yes, sir.
जी बेटा, अगर ये मेरे पास impulse response है, I'm talking about this second example, and I have placed nd is equal to 2. So h of n is something like that. That's the impulse which is delayed by 2 samples. And now that's the impulse response. This is the impulse response of this system. Now my input is this. What will happen to output?
Sir, exponential e की power.
What will happen to output? I'm not talking about the frequency response of the system. I'm just talking if this is going in, whose frequency response is this thing. Sorry, the impulse response is this thing. What will be y of n? I'm only interested in time domain signals. I'm not talking about frequency.
Convolutions are both x of n and h of n.
And what will happen? You need to do the convolution or something obvious?
So, I would get 3.
Sorry? What will happen to the output? लेक्चर्स बेटा डाउनलोड करके पढ़ते हैं
सर जो सिग्नल है वो 2 पे शिफ्ट हो जाएगा
ग्रेट सो दिस इज ये 2 की शिफ्ट है तो दिस इंपल्स व्हेन कन्वॉल्व विद दिस ये सिर्फ और सिर्फ इसको शिफ्ट कर देगी ये इधर आ जाएगा 1 2 and 3 दैट्स द ओनली थिंग एक्स ऑफ एन अंदर गया इंपल्स रिस्पांस क्या है जी इंपल्स रिस्पांस ये है द इंपल्स शिफ्टेड राइट टू 2 सैंपल्स and as a result of that your output will be this. Now we are interested in knowing the frequency response of the system. So again there are 2 ways. One way is that you take the formula h of exponential j omega n is equal to minus infinity to infinity h of n exponential minus j omega n. So that would be 1 into exponential. 1 kahan se aaya? 1 is coming from here at the location nd exponential minus j omega n is replaced with nd and the magnitude is 1 so that's the magnitude and phase response is minus omega nd this portion with a negative sign that's the phase response of the system. So whenever you will be watching it in the properties of the DTFT that whenever you are delaying your signal with some sample delays those will come as the phase response of the system and that would be proportional to the delay in your time domain signal. You will be watching it in your discrete time Fourier transform properties portion. Okay, there was another example that this is the situation. It is impulse response is given and you are interested in knowing the frequency response of the system. So h of exponential j omega is equal to 0 1 because ideally it is from minus infinity to infinity, but right now as the samples at 0 and 1 so we have written 0 1 h of n exponential minus j omega and that's the DTFT formula. This should be as the back of your hand. ठीक है ये हर वक्त ज़हन में रहना चाहिए कि ये क्या चीज़ है. Now we have just opened it up. h of n is equal to 1. Location क्या है 0 plus 1 location क्या है n की location क्या है that is 1 and we have ended up at 1 plus exponential minus j omega. We have taken exponential minus j omega by 2 as common and as a result this one is exponential j omega by 2 because when you will be multiplying these two that would be 1 and here you will be taking exponential minus j omega by 2 but because when you will be multiplying both of these you will be getting this thing exponential minus j omega by 2 and this is nothing but 2 cosine omega by 2. That's the magnitude component and the phase term is which is associated with exponential j के साथ जो चीज है that is minus omega by 2. Any questions? जी बेटा, any questions? आवाज आ रही है मेरी सबको?
यस सर, आवाज आ रही।
यस सर,
आप कौन सा? ये
आ रही है
36
सर
बंदे
आवाज।
बैठे हुए हैं, जवाब कोई दे दे यार मुझे। जी अली अकरम साहब, आवाज आ रही है मेरी?
यस सर, आ रही है।
कोई क्वेश्चन है आपका?
नो सर।
जी मुझे आप बताइए कि मुझे अगर फ्रीक्वेंसी रिस्पांस फाइंड आउट करना हो किसी भी सिस्टम का तो मैं क्या करूंगा? जी अली, Ali Akram, I'm waiting from your answer. Ali Saab, are you listening? Abdul Majid Saab.
जी सर।
जी सर, बताइए।
सर जब फ्रीक्वेंसी रिस्पांस फाइंड करना होता है तो कन्वोल्यूशन कर रहे होते हैं तो जो इम्पल्स के दरमियान अंदर जो शिफ्टिंग होती है वो ट्रांसफर हो जाती है एक्सपोनेंशियल के अंदर।
बेटा तवज्जो के साथ सुना करें प्लीज। ओके, स्क्रीन शेयर हो रही है ना बेटा? स्क्रीन शेयर हो रही है?
जी सर।
यस सर।
चलें जी, ये फ्रीक्वेंसी रिस्पांस हमने देख लिया था। लेट्स मूव फॉरवर्ड एंड नाउ दिस इज सम एग्जांपल ऑफ filtering example है कि how the signals are behaving in time domain and frequency domain. Suppose हमारे पास ये एक सिग्नल है जिसको हम कह रहे हैं this is x1 of n, और x1 of n क्या चीज है? एक साइनोसॉइडल सिग्नल है, suppose of certain frequency ओमेगा नॉट का। ठीक, सिग्नल है टाइम डोमेन में, ये मेरे पास एक सिग्नल पड़ा हुआ है। फ्रीक्वेंसी डोमेन में एक दूसरा सिग्नल है विच इज हाई फ्रीक्वेंसी सिग्नल, इसको मैंने कह दिया दिस इज x2 ऑफ n। और सपोज कर लेते हैं क्योंकि ये हाई फ्रीक्वेंसी सिग्नल है, आई एम सपोजिंग दैट दिस इज अ नॉइज एंड दैट नॉइज इज बीइंग एडेड टू माय नॉर्मल सिग्नल विच वाज द डिजायर्ड सिग्नल। ये इसके अंदर ऐड हुआ एंड दैट्स द कंपोजिट सिग्नल जो कि x ऑफ n बन गया, जिसके अंदर दोनों कंपोनेंट्स जो है मौजूद हैं, द डिजायर्ड कंपोनेंट भी है और अनडिजायर्ड कंपोनेंट जो नॉइज है वो भी मौजूद है। एंड माय इंटरेस्ट इज टू रिमूव this x2 of n, the noise, the high frequency component from my desired signal, and I have performed some filtering operation, and as a result of that I have got this y of n which is my desired signal. ठीक है, problem clear है? So that's the time domain version of everything. x1 of n, which was the the desired signal, a lower frequency signal. It was the higher frequency signal resembling noise, and x of n is the composite signal which is x1 of n plus x2 of n. Sample by sample जो है इनकी एडिशन हुई है तो सुपर इम्पोज हुआ है मेरे लो फ्रीक्वेंसी सिग्नल के ऊपर मेरा हाई फ्रीक्वेंसी सिग्नल, एंड आई हैव गॉट दिस। and as a result of filtering operation क्या होता है? filtering operation is y of n is equal to x of n convolved with h of n, and h of n is what? h of n is the impulse response of the filter, which can be IR or FIR. I have implemented some filtering operation on x of n, and I have obtained this y of n, which the aim was to remove the high frequency component, and this has been done sufficiently well. So let's see it, the same phenomena in frequency domain. So what will be happening in about x1 of n? x1 of n frequency domain में क्या होता था, क्या करते थे आप? अगर मैं इसे कहूँ, इसका frequency domain में किस तरह की चीज आपको नजर आएगी? इस तरह की impulses आपको नजर आती है, ठीक है, उस particular frequency पे. Suppose this is minus omega naught, this is omega naught. ठीक, so similar things are happening. So that's the filter. ये मेरा frequency response है h of exponential j omega, and this is a low pass filter. Why low pass filter? Because I have to remove the high frequency component. As I'm saying that whenever in time domain you have got many oscillations, it's a high frequency signal, and I have to remove it. So that's why I'm using low pass filter. The lower frequency component is being passed and the high frequency component is being attenuated. And that's my x of omega, which is nothing but capital X of omega, the frequency response of this composite signal, of this component composite signal, this one, where x of n is equal to x1 of n plus x2. So in दोनों signal को जब हमने superimpose किया, we have got this, and now this one is the frequency response of this composite signal, where we are watching clearly two frequencies. One is this one, the lower frequency component, and the upper frequency component, and we are showing it from 0 to pi. So there will be the replica of this on the minus pi side as well. The lower frequency component and the higher frequency component, the replica is coming from the definition of this thing. Now what is happening whenever you are multiplying it in so what here in time domain we are convolving, and you will be watching that in frequency domain it is nothing but x of exponential j omega into h of exponential j omega. Both the frequency response will be multiplied, and as a result of that, what is happening, that this frequency component will be passed, and this frequency component, because it's being multiplied with the attenuated portion of the filter or 0, so that portion is vanished. So as a result, you have obtained in frequency domain only one frequency component, which is shown here. Questions, please. That was just you that what is happening in time domain and what is happening in frequency domain, and you must be visualizing the same simultaneously the procedures in both time and frequency domain. Any questions, beta? बच्चे आवाज नहीं आ रही या वैसे हर चीज क्लियर हो गई है, कॉम्प्लेसेंसी है? कुछ थोड़ा सा एक बंदा जो है वो जरूर रिस्पॉन्ड करता रहे, सो दैट कि एक बंदा जो कंप्यूटर के दूसरी तरफ बैठा हुआ है, he shouldn't think himself a fool. जी सीआर बैठे हुए हैं?
यस सर, क्लियर है, आवाज आ।
आप कौन साहब हैं?
सर मोहम्मद हसन गफूर।
जी मोहम्मद हसन गफूर, क्लियर है बेटा?
यस सर।
ओके, एक बंदा जो है ना वो प्लीज रिस्पॉन्ड करता रहा करे। और सीआर का क्या नाम है बेटा? सीआर का?
सर मैं ही हूँ, मैं रिस्पॉन्ड कर दूंगा आपसे।
अच्छा चलें, आप रिस्पॉन्ड कर दिया कीजिए ताकि कुछ ना कुछ जो है ना वो हालात बेहतर है। चलें आगे।
यस सर।
ओके ठीक है जी। सो अगेन now that's the frequency response of LTI systems. In fact, you have done it before, just revise it, that if you are interested in knowing the frequency response of this system, y of n is equal to x of n minus nd. The impulse response is this thing, h of n is equal to delta of n minus nd. So that's the delay we are introducing. I have asked the question about this from you as well. So that's an impulse response of the system. किस तरह की चीज है? इस तरह की चीज है। So 2 पे आपका that's the impulse response of the system if nd is equal to 2. And if you are interested in knowing the frequency response of the system, one way is to make x of n exponential j omega n. So what you are doing, y of n will be equal to exponential j omega n minus nd. You have replaced n minus nd, and this is equal to what? This is equal to exponential j omega n and exponential minus j omega nd multiplication sign. That was your complex exponential, the eigenfunction. You throw it out, and the rest is the frequency response of the system. अगर आप interested हैं in knowing the magnitude of this, the magnitude is 1, because इसका exponential जितनी भी terms हैं उनका magnitude 1 होता है. So that's the magnitude, and the phase responses जो कि इसके साथ associated है exponential j के साथ. So that is minus omega nd. So that's the phase response of the system, minus omega nd. Similarly, this is the system y of n is equal to CR. ठीक है?
Yes, sir.
Okay, so the other system y of n is equal to x of n minus minus 1. अगर impulse response की बात करें तो this would be the impulse response. इसमें गलती हो गई थी अभी दूसरी क्लास में. So that's the situation. Okay, so that's h of n is equal to delta of n minus delta of n minus 1. एक पल्स जो है सैंपल ऊपर है और एक सैंपल जो है वो -1 पे है. You can do in both ways. You can use this equation, which is h of n omega is equal to n is equal to minus infinity to infinity h of n exponential minus j omega n. That's the definition of dtft. Either you use this equation, or you can make x of n is equal to exponential j omega n, and then y of n will be equal to exponential j omega n minus exponential j omega n minus 1. Exponential j omega n को आप कॉमन कर लीजिए. The rest will be 1 minus exponential minus j omega. और इस 1 minus exponential j omega को आप ये कर सकते हैं. You can take exponential minus j omega by 2 कॉमन ले लिया है. Then exponential j omega by 2 minus exponential minus j omega by 2. क्योंकि नेगेटिव है साइन दरमियान में, सो नेगेटिव साइन के लिए हम इसे साइन की तरफ लेके जा सकते हैं. बिकॉज कोसाइन ऑफ ओमेगा इज इक्वल टू एक्सपोनेंशियल j omega प्लस एक्सपोनेंशियल माइनस j omega डिवाइडेड बाय 2, एंड दिस इज साइन. तो यहाँ पे क्योंकि नेगेटिव साइन रखा हुआ है, अच्छा ये नेगेटिव साइन है, तो इसको हम डिवाइडेड बाय 2j और मल्टीप्लाइड बाय 2j कर देंगे. सो दैट्स व्हाट, दैट्स साइन ओमेगा बाय 2, एंड दिस 2 विल बी written here. So 2 sin omega by 2, that's the magnitude component, and j exponential minus j omega by 2, that is in fact the phase component. And j is what? J is equal to pi by 2. ठीक है, phase की terms में whenever you will be watching j term, you will be replacing it with pi by 2 minus omega by 2. From where omega by 2 is coming? Exponential minus j के साथ जो term है, that is minus omega by 2, और that is pi by 2 minus omega by 2. So whenever you will be plotting magnitude, you will be plotting here 2 sin omega by 2. That would be the magnitude response. And whenever you will be, and अभी थोड़ी देर में आप देख लेंगे कि ये प्लस पाई और माइनस पाई के दरमियान है, because it's periodic. And similarly, whenever you will be phase of that, so that's again plus pi और minus pi के दरमियान है. शिफ्ट आ जाएगा उसके अंदर प्लस पाई, और ये भी प्लस पाई और माइनस पाई के दरमियान ही जनरली हम प्लॉट करते हैं. So right now I am not plotting it in chapter number 2, but there will be extensive plotting of that in chapter number 5. So just a shift of pi by 2 होगी आपके पास जब आप ये प्लॉट कर रहे हैं. जी CR, any question बेटा?
ठीक है सर.
So the frequency response of LTI systems, you know it now, that h of exponential j omega by definition, this is the DT equation of the system. They're claiming that this is periodic with period 2 pi. So if I have to confirm my claim, what I will be doing, I will be replacing omega with omega plus 2 pi in the same equation. So h of exponential j omega plus 2 pi will be what? That would be k is equal to minus infinity to infinity h of k. उसी तरह से आ गया exponential minus j omega is replaced with omega plus 2 pi into k, and now you will be opening it. So ये चीज क्या हो जाएगी, exponential minus j omega k, exponential minus j omega k, which is written here, and the second thing is exponential minus j 2 pi k. That's the term, and that's in fact equal to 1. Why? Because exponential minus j omega j 2 pi k will be equal to cosine 2 pi k minus j sine 2 pi k. This term is equal to 0 and this term is equal to 1. So that's why exponential minus j 2 pi k is equal to 1, and the rest is h of k exponential minus j omega k, which is nothing but similar to what was h of exponential j omega. So we conclude that whatever we are watching h of exponential j omega, अगर हम plot करते हैं, so whatever we are watching at omega is equal to 0, we will be watching the same thing as 2 pi, we will be watching the same thing as minus 2 pi, and similarly minus 4 pi plus 2 pi, because of this periodicity. So if this is the situation here, you will be watching the multiple copies here because of this property, ये periodicity जो आपके पास मौजूद है. Questions please. जी बच्चा. सीआर
ठीक है सर. यस सर,
कोई
ठीक है जी.
कोई और स्टूडेंट सीआर के अलावा भी है, कोई और बंदा रिस्पॉन्ड कर दे, कोई क्वेश्चन पूछ ले, कोई कंफ्यूजन हो तो यू आर मोस्ट वेलकम.
No, sir, कोई नहीं.
चल, and then we move to, after periodicity we move to the convergence of frequency response, and it's the same thing what we have talked about the stability context में हमने बात की थी. Suppose some system is given to you, the impulse response is given, and it was asked that whether the system is stable or not. What you were doing, you were taking all the samples of HFN, you were taking and the absolute sum of from minus infinity to infinity, and if it was lesser than infinity, you were saying that the system was stable. So we are using the same thing here as well, that for another way of saying the same thing, that the convergence of frequency response, of course the system will be stable, the frequency response will be converging. So h of exponential j omega, absolute value of that will be the absolute value of this expression, and exponential minus j omega की जो absolute value है, the magnitude है, that is always 1. So now we are only concerned with this thing. K is equal to minus infinity to h of k absolute values, and if this value, which we have written here as well, if this value is lesser than infinity, then we will be saying that our frequency response is converging, and it's written the same thing as k. It's the same condition for stability. So whenever we are talking about the DTFT exists, will converge. Okay, the DTFT converges. So everything is same. All these three statements are same. Whenever we have a stable system, it means that discrete time Fourier transform of that system is existing, or the DTFT is converging. ठीक हो गई बात? Should we move forward?
Yes sir.
Okay. So now the discrete time Fourier transform, by definition, it is x of n is equal to okay. So by definition, x of exponential j omega is equal to n is equal to minus infinity to exponential minus. So the important thing is that you can have any h of n, you can have any x of n, you can have any y of n, and associated with that are the frequency responses. So that would be h of exponential j omega. Here you will be getting x of exponential j omega, and here you will be getting y of exponential j omega. The frequency responses of these systems, the Fourier transform, in fact, of all these. At this time, it's talking about the frequency response, the definition of the x of n. इसके बारे में बात कर रहे हैं. But it's the same. By definition, everything will be the same. So if we are interested in knowing y of exponential j omega, that is nothing but n is equal to minus infinity to infinity y of n exponential minus j omega n. ठीक है, कोई भी आपके पास चीज होगी तो x of n मौजूद होगा तो you can get x of exponential j omega. If you have h of n, you can get h of exponential j omega, and if you have y of n, you can get y of exponential j omega n. So here we are talking about x of exponential j omega. That's the DTFT formula, जिसको हम direct transform भी कहते हैं. You are quite familiar with that. And x of n, अब अगर आपको वापस चाहिए, as you were doing it in your discrete continuous time Fourier transform, that you are moving from x of t से आप move कर रहे थे x of j omega की तरफ. And अगर आपके पास x of j omega है and you are interested in knowing x of t, so what to do in that case? That was the inverse continuous time Fourier transform. So here as well you have the inverse DFT formula. 1 over 2 pi minus pi to pi x of exponential j omega n d omega. And remember that here the complex exponential is with plus sign, and we are integrating it from minus pi to pi. And what's the reason of integrating it from minus pi to pi? Why we are not using a summation and we are doing the integration? What's the reason? Any volunteer? जी बेटा सीआर, किसी का नाम बताइए. मुझे तो नाम अभी से सिंडिकेट बी के नाम नहीं आते. आप किसी का नाम बताइए, उससे पूछते हैं फिर.
सर अहमद मसूद.
जी अहमद मसूद भाई, आप बताइए.
सर मुझे नहीं पता.
हाँ, जल्दी जल्दी जवाब दिया करें, कोई बात नहीं. अगर नहीं भी पता तो रिस्पांस जो है ना वो इमीडिएट होना चाहिए कि सर आई डोंट अंडरस्टैंड. कोई मसला नहीं, लेकिन जरा जल्दी से, मतलब सुन हो के बैठे ना रहा करें. जी
सर
आप
x of e j omega जो है वो कंटिन्यूअस है इस वजह
ग्रेट,
से.
जबरदस्त. कौन साहब हैं आप?
सर हसीब.
हसीब, थैंक यू वेरी मच. एंड हसीब आंसर्स इज करेक्ट कि x of exponential j omega क्योंकि continuous quantity है, so that's why we are not summing it, we are not using this sign summation here in this formula, and we are integrating it from minus pi to pi because we have already talked about the periodicity of this thing. ये जो चीज है h of exponential j omega या x of exponential j omega या y of exponential j omega, that's a periodic thing, and with period जो कुछ भी आपको actually जो unique चीज आपको नजर आ रही है, that is between minus pi and pi. Otherwise everything will be repeating. So that's why here we are using minus pi to pi जो है वो आप use कर रहे हैं integration के लिए, because that's the unique version of the signal you will be getting here. As it is continuous, we are using the integration sign, and as a result of that you will be getting your samples of your x of n inverse transform. ठीक होगी बात? हाँ जी, yes, no,
Yes,
maybe.
sir.
हाँ, शाबाश.
Yes, sir.
ओके, एक्टिव होके बैठे हैं. कोई मैं पिछले 2 घंटे 3 घंटे से यही काम कर रहा हूँ. पहले मेरी सिंडिकेट सी के साथ क्लास थी. थोड़ा सा मैं आपसे भी तो चाहता हूँ ना कि आप एक्टिव हो. ओके, एग्जिस्टेंस ऑफ DTFT. It's the same thing which we have already talked. The DTFT existence, stability, convergence, it's the same thing. So if you are given a signal and wants to know कि इसका Fourier transform exist करता है या नहीं, there will be a same condition. You will be taking the samples of your x of n, and if the absolute values of those samples are lesser than infinity, it means कि आपका DTFT जो है वो exist करता है. It is the same thing as you are saying that your DTFT converges. Convergence means that the DTFT exists. और जब हम सिस्टम के कॉन्टेक्स्ट में बात करते हैं, that is when we are talking about HFN, उस केस में इसी DTFT को या इसी फोरियर ट्रांसफॉर्म को हम कहते हैं कि अगर वो एग्जिस्ट कर रहा होता है तो हम कहते हैं कि हमारा सिस्टम जो है वो स्टेबल है. ठीक है, so it's the same thing whether it is stability, whether it is convergence of DTFT, whether it is existence of DFT, the conditions will be same. That would be on the impulse response or the time domain version of the signals, that you will be summing up absolute samples of that signal or that system, and if those are lesser than infinity, you will be saying in the system context, you will be saying that the system is stable, and in the signals context, you will be saying that the Fourier transform exists or the Fourier transform converges. Any questions, better? जी जनाब. चलें आगे.
Yes, sir.
Okay. So this is an example of a moving average filter, and I will be doing it tomorrow. ठीक है, अभी हमने उनके साथ तो किया है सिंडिकेट सी के साथ, लेकिन आपके साथ मैं इसको जरा थोड़ा सा कुछ लोग, क्योंकि कल तो क्लास होनी है ना, कल ऑनलाइन क्लास तो नहीं है ना, कल तो हम क्लास में ही होंगे. क्या ख्याल है सीआर? कल फेस टू फेस मोड में क्लासेस होंगी ना?
Yes, sir. Inshallah.
इंशाल्लाह ताला. तो ये एग्जांपल हम उधर करते हैं और लेट्स डू इट. ये जो आपके सामने है, दैट्स a raised to power u of n. मैं दोबारा इसको यहाँ कर देता हूँ. सो एक चीज आपको गिवन है, दैट इज x of n. इस एग्जांपल को सॉल्व करते हैं. x of n is equal to a raised to power n u of n, and we are interested in knowing the exponential, यानी this one. जी जनाब, any idea, any volunteer to guide me किस तरह से इसको सॉल्व किया जाए? जी मेरा ख्याल है फीमेल स्टूडेंट थी, क्या नाम था? माहिताबा सिटिंग. जी, any female student can answer this question. How to proceed for this example? फातिमा पीरजादा, आप बताइए.
सर बाय डेफिनेशन डीटीएफटी निकालेंगे.
बेटा पहले यही आवाज मेरी नहीं आ रही थी आपको?
यस सर.
पहले नहीं आ रही थी?
सर आ रही थी.
तो फिर उस वक्त जवाब क्यों नहीं दिया? जी बोलें, क्या करें? क्या कह रही हैं आप? बोलती जाएं आप.
बाय डेफिनेशन डीटीएफटी निकालेंगे.
जी बताएं ना, आप मुझे गाइड करें, मुझे नहीं आता ना.
सर समेशन
क्या लिखूं? समेशन जी.
सर 0 to infinity. 0 to infinity.
क्यों 0 to infinity किस वजह से लिखवा रही हैं?
सर यूनिट स्टेप फंक्शन है.
गुड, जबरदस्त. और किस चीज के लिए जा रहे हैं? n is equal to 0
Yes.
to infinity. गुड फातिमा. एंड व्हाट एल्स?
आगे अपना सिग्नल को एज इट इज लिख देंगे.
सिग्नल को ये लिख दूं, यूं लिख दूं?
सर नहीं, यूनिट स्टेप को हटा दें अब.
गुड. सो इसको रिमूव कर दिया because that has been incorporated in this summation. x of exponential j omega, that would be equal to this. And कुछ और लिखना भूला तो नहीं हुआ?
सर e raised to power minus j omega n.
e raised to power minus j omega n. ऐसे ही है जी. चलें अब आगे क्या करूं?
सर अब इसको सॉल्व करना है।
करें ना, बताएं, आप बताएं, मुझे नहीं आ रहा ना। इसको मैं यूं लिख सकता हूं, a एक्सपोनेंशियल माइनस j ओमेगा रेज टू पावर n, लिख सकता हूं ऐसे।
यस सर।
अब चलें आगे, बताएं आगे क्या करें। You remember the formula? A raised to power k, k is equal to n1 to n2, and that was nothing but 1 minus a raised to power n1 minus a raised to power n2 plus 1. You can use this. ठीक है?
यस सर।
Okay, do it. क्या होगा? जी फातिमा बोलें प्लीज।
एक सेकंड सर।
ए, ठीक है, सो क्या हो जाएगा 1
सर
माइनस ए एक्सपोनेंशियल जे ओमेगा, ठीक है, और ऊपर
Yes.
क्या हो जाएगा a raised to power 0, that would be equal to 1, ऐसे ही है,
यस सर।
माइनस a exponential minus j omega raised to power infinity plus 1. So what's the final answer? ये एग्जांपल हम पहले कर चुके हैं क्लास में, आपकी स्लाइड्स में मौजूद है।
सर 1/1 minus a e raised to power minus j omega.
Okay, जबरदस्त, 1/1 minus a exponential minus j omega, but with a condition that a is lesser than 1, because only when a is lesser than 1, this portion will approach to 0. When a is lesser than 1. So it's a very important thing. You will be utilizing this thing again and again, that x of n का discrete time Fourier transform जो आपने find किया है, which is exponential j omega, that is nothing but यानी a raised to power n u of n का, that is 1/1 minus a exponential minus j omega, with the condition that a is lesser than 1. ठीक हो गया जी?
Yes sir.
Okay. So we will be starting properties tomorrow, and we will be doing this example tomorrow as well. Okay, thank you very much. I close it.